Okay, so this is part 2 of the OCR overview or topic overview. Obviously following on from part 1, which covered the year 9 topics. I've kept the video down to 15 minutes, so this is the year 10 topics, which are also going to be in the first physics paper. All right, and will also feature in the year 10 mocks. In year 10, you would have been introduced to P2.2, which is forces. Okay, you were introduced to Newton's laws, Newton's first law, second law, and third law. All right, you were introduced to the idea that we can represent forces with arrows. There are various things you need to revise here. I would revise Newton's laws, okay, as follows. We've got Newton's first law, okay, the idea that an object will carry on doing what it's doing. Its motion will not change unless a force is acted upon it. So if an object is moving and its speed increases or decreases or it changes direction, a force must have acted upon that object. So Newton's first law is we're talking about one object. We're thinking about the overall force on that object. Okay, if there is an overall force on that object, it will be accelerating, which means an increase or a decrease in speed or a change in direction. Okay, so Newton's first law, one object, and we're thinking about the resultant overall force. If you're going to draw force arrows, use a ruler. Okay, the length matters. The length is the size of the force. So if you're drawing forces that are equal in both directions, okay, you need to draw them equal. So measure them properly. Use a pencil. Okay, the resultant is the overall force on an object. Okay, we're taking all the forces into consideration and we're going to summarize them as one overall resultant force. Okay, if the forces are balanced, the object will continue doing what it was doing. It's going to continue with constant speed and direction. It does not necessarily mean it is stationary. Do not fall for that trap. An object that's traveling at constant speed and direction will have equal forces acting upon it. Okay, so be careful before you say the word stationary. If we're talking about Newton's second law, well, that's about talking about the relationship between force and mass on acceleration. Okay, we're still talking about one object. We're just developing our understanding of Newton's first law a little bit. All right. If there is an overall force on an object, it will accelerate, and we can talk about Newton's second law. Newton's third law is about interaction pairs. Newton's third law is all about the interaction between two objects. So if you're talking about two objects interacting, okay, you need to have two objects to be talking about Newton's third law. Okay, if you're talking about interaction pairs, we want to think about the phrase equal and opposite. Okay, the interaction between objects is equal and opposite. Okay, that is often the answer. Equal and opposite forces. Newton's third law. You need to have two objects for that to be the case. Okay, you need to revise that. Obviously, forces is a large topic. I'm not going to cover it in much depth here. Okay, but that's the basic understanding. We introduced the idea that work done equals the force of an object. Okay, multiply the distance that object has been moved. Okay, the distance is always measured in the direction of force. The work done, you need to understand, is the same thing as energy transferred. Okay, so sometimes we talk about the word energy, sometimes we use the word work. You need to understand that work is the same thing as energy, essentially. They're both measured in joules. Okay, this comes up all the time. Okay, if we're in a gravitational field, there's always going to be a force downwards, and it's called weight. It's not gravity. Okay, you should label that downward force as weight. Typical forces in the other direction, that might, for example, if this was a falling tennis ball, typical forces acting, if this is a falling tennis ball, would be air resistance, but air resistance, remember, only occurs when there's a velocity. Okay, weight will be acting upon that tennis ball, even if it's on a table. Weight is always going to be a downward force. We went on to think about the application of forces. Okay, you might see the word load. Load is the same thing as a force, really. Okay, we use the word load when we're applying a force. For example, applying a mass to the end of a spring. You need to know that. You need to remember that you did a practical by applying a mass to a spring, and if you apply a load to a spring, it will extend. The extension is the change in length. The change in length is important. You need to know that if you've got a force extension graph, the straight part of the graph obeys Hooke's law and represents elastic deformation. Okay, elastic means it will return to its original size and shape when the force is removed. Okay, you have to say that. If we get a curve, okay, we're no longer obeying Hooke's law because it's curved and it's representing plastic deformation. That's when it doesn't completely go back to its original size. So if you overstretch your spring, when you take the load off, it will be longer than it was before. And that means we've no longer got elastic behavior because we're no longer returning to its original size. So know these words, know what Hooke's law is. That's the straight part of the graph. Know what elastic means, it returns to its original size and shape. Know that the opposite elastic is plastic. Okay. Know that extension is about the change in length of the spring, for example. We can calculate the spring constant from the gradient of the straight part of the graph. We can calculate the energy stored in a spring by calculating the area under a graph. Okay, so when the extension is 40 millimeters on this particular graph, there is this much energy stored in it. I have to calculate the area of that triangle. Okay, so area gives me energy stored. The gradient gives me the spring constant, okay, which is the stiffness of the spring. Then you would have gone on to P3.1, static electricity, which is all about understanding how like charges repel, opposite charges attract. Okay, we talk about the fields around charged particles. When we talk about fields, we're talking about non-contact forces that occur. Okay, we can charge things up like a strip of plastic, and we can attract pieces of paper. We need to explain that if something is attracted to something else, it must be because it's got opposite charge. If something is repelled by something, it must have like charge. If you've got a question on static electricity, know these phrases here. Like charges repel, opposites attract, electrons are transferred from one object to another. Please do not say positive electrons. There's no such thing as a positive electron. Please do not say that protons are attracted or transferred from one object to another. It's always going to be electrons being transferred. Okay. Another big topic in year 10, circuits. Right. You need to know about series circuits. Okay, here we've got two filament lamps there in series, one after the other. Okay, if we're going to put an ammeter in that circuit, ammeters have to be connected in series, and we can connect an ammeter wherever we like in a series circuit because the current in a series circuit is the same everywhere. Know the rules for a series circuit. Know the rules for a parallel circuit. Okay, you need to know that in a parallel circuit, the overall resistance is reduced. Okay, you need to know that current splits at a junction. Okay, if I've got a certain amount of current, I've measured at this ammeter here. Okay, if I had an ammeter here, I would measure different current. If I had an ammeter there, I'd have a different current, but they would add up to be the same as what I had to start with. Okay, so if I've got 5 amps there, which is a lot. Okay, if each of these lamps are identical, then it's going to be an even split. I'll have 2.5 there and 2.5 here. Okay, current will come back together again at X. I will have 5 amps again. So the rules for a series circuit are different to the rules for a parallel circuit. Okay, you need to know the rule for voltage. Okay, you need to know the rules for current, and you need to know the rules for resistance. So very, very, very quickly, okay, in a series circuit, voltage will be divided across each component. Okay, the current will be the same everywhere. The resistance adds up. Okay, for a parallel circuit, okay, voltage across each pathway is going to be the same. Current splits and the resistance is reduced. Okay, so you need to understand that. Okay, the resistance when we have 2 lamps in parallel is actually less because the electrons have got 2 pathways now, adding a lane to a motorway. Okay, it's easier for the current to get from one side to another because it's got more than one pathway. Okay, so it's not necessarily something you would guess correctly, but it does make sense if you think about it hard enough. Okay, the voltage is the same across the pathway, the current splits, the resistance is decreased. Okay, so basically the rules for a series circuit in terms of V, I, and R are opposite than those rules for a series circuit. Okay, series and parallel. Learn those rules. All right. Know the difference between series and parallel. By the way, a voltmeter must be placed in parallel, and they like to test you on this. Okay, a lot of students get the ammeter and the voltmeter the wrong way around. Okay, so know that an ammeter has to be in series, a voltmeter has to be parallel to a component. It has to be comparing one side to the other. You also need to understand that different components behave differently. Okay, there's a classic graph, which is this one here. If you've got temperature on the x-axis, we're talking about a component that is sensitive to temperature, so we're talking about a thermistor. Whereas if you've got a similar looking graph, but it's got intensity or brightness of light on the x-axis, then we're talking about a light dependent resistor. Okay, they like those because the graph looks similar and they know you're going to be confused. So don't be confused, revise it. You need to know some symbols. Okay, so you need to know that's a diode, that's a resistor, this is a lamp. You might call it a bulb, but it's better to call it a lamp. And this one here with the arrows coming in is a type of resistor because it's got the rectangle. It's the LDR, the light dependent resistor. The arrows coming in represent light. Okay, circuits, it's a big topic. It's a confusing topic, but at the very least know your difference between a series and a parallel circuit. Okay, know that V equals IR is the classic equation that you're likely to have to use. Okay, please use Quen to show you working. And you should also have covered magnetism. Okay, magnetic fields are usually quite good at, but know that when we're talking about a biomagnet, for example, we've got the north and the south pole. Field lines go from north to south, so the arrows will be going north to south. Be careful, follow it, make sure we're going from north to south. If they're coming out of the pole, it must be a north pole. If they're coming into a pole, it must be a south pole. Okay, so north to south. Biomagnet is straightforward. You don't have to draw too many field lines, but you need to know that the field lines must never cross. They're continuous. The magnet is strongest at the poles where the lines are close together. Okay, we can also make magnetic fields with a current through a wire. Okay, so if we have a wire and we put a current through it, current always goes positive to negative. You need to know that there's going to be a field around that wire. I can use the right hand rule, thumb in the direction of the current, fingers wrapped around, tell me that the field is going to be going that way around that wire. Okay, so you might want to revise the right hand rule. Just know that there's a field around that wire. Okay, so if we have a current going through a wire, we get a magnetic field. That's cool because we can turn it on and off. We can make it stronger by having a larger current. I can have more wire. Okay, so I can have more coils. So I can make that field stronger. I can control it. All right. You need to remember that we can make an electromagnet by taking a magnetic material and wrapping wire around it. Okay, more coils, stronger magnet. Okay, I'm going to take that wire and I'm going to connect it to a battery or a power supply. Okay, I've now got an electromagnet as long as this core is a magnetic material. That means it has to be iron, cobalt, or nickel. 3 magnetic materials it can be. Not copper, not aluminium, okay, not magnesium. Okay, they are not magnetic materials. They would not make my electromagnet work. Okay, an electromagnet, I can make it stronger. More coils, more current. I can turn it on. I can turn it off. Okay, that's useful. I can use that in a scrapyard, and I can sort out a pile of mixed metal, couldn't I? I can pick out the iron, the cobalt, the nickel, and leave behind the aluminium. Okay, so there are many uses for electromagnets. Okay, triple students will go on to understand how that concept is used in motors, but I'm not going to cover that here. Okay. I hope that's useful. It's very brief. Obviously, you need to know more than that, really, but at the very least, know the topics you are going to expect to have to grapple with in the exam. So, yeah, there are ways of getting more marks than other people. Show you're working, okay? You read the question carefully. Use the keywords to help you understand what they want, right? Use a diagram. If they give you a graph, use the graph. It's there for a reason. If they give you a diagram or a table, look carefully. What does that table tell you? Can you see a pattern? Can you quote numbers from it? Okay. If you can do something with that information they've given you, write it down to show the examiner that you have used that information. Okay. Get as many marks as you can. If you don't write it down, they won't give you credit for it. They are not going to be able to read your mind.